and thank you for the successors you have been having. And we hope that more beautiful ants will join this platform. I want to please tell, I don't know whoever that is mic is on, so please mute it so that there will be no any interference when the lecture is going. Mr. Sagir, I congratulate you for taking the bold step to present this presentation.
Thank you, sir.
I wish you all the best. Thank you and wishing you a good presentation. Thank you.
Thank
Good
you, sir.
morning.
Thank you, sir. Good morning, the chairman, all members here present. My name is Sagir Ibrahim. I'm here today to present my work on product of quasi-idempotent final semi-group or full order preserving transformations. This is a joint work with Dr. A.T. Imam and other three co-authors, and this work was published in the Journal of Algebra and Discrete Mathematics, volume 35, issue number 1 in 2023. This is the outline of the presentation, the abstract. Let Xn be a finite set and On be the semi-group full order preserving transformations on Xn. A transformation alpha is called an idempotent if alpha is equal to alpha square, and a non-idempotent element whose square is an idempotent is called quasi-idempotent. In this work, we characterize quasi-idempotent elements in the semi-group full order preserving transformations, and we showed that the semi-group of full order preserving transformations is quasi-idempotent generated. Moreover, we obtain an upper bound for the quasi-idempotent rank of On. That is the cardinality or minimum generating set of quasi-idempotent to be the ceiling of 3 into n minus 2 over 2, where the ceiling of x denote the least positive integer m, such that x is less than or equal to m less than x plus 1. These are the basic definitions required to understand this work. By a semigroup, we mean a non-empty set S that is endowed with an associative binary operation, a subsemigroup. A non-empty subset T of a semigroup S is called a subsemigroup S if it is closed under the same binary operations as that of S. That is, for all xy in T, the product xy lies in T, a regular semigroup. An element A in the same group S is called regular if there exists X in S, such that AXA equal to A. The same group S is called regular if all its element is regular. That is, for every A in S, there exists X such that AXA equal to A. We consider a finite set, then a mapping alpha of alpha mapped to Xn is called partial transformation of Xn if domain of alpha is a subset of Xn, and is called full transformation if domain of alpha is equal to the entire Xn. The set of all full and partial transformations of Xn form a semigroup under composition of mapping and are respectively denoted by Tn and Pn in this work. So anywhere we see Tn, we are referring to the set of the semigroup of full transformations, and anywhere we see Pn, we are referring to the semigroup of partial transformations, order preserving transformation. A full partial transformation is said to be order preserving if for every xy in the domain of alpha, x is less than or equal to y implies the image of x is less than or equal to the image of y. Thus, the full order preserving transformations is a regular subsemigroup of Tn. That is, the full order preserving transformation is a regular subsemigroup of the full transformation semigroup. That is, for all alpha in On, there exists beta in On, such that alpha is equal to alpha. And this semigroup full order preserving transformation is denoted by this equality, that is alpha in sin n, so that for every xy element in Xn, x is less than or equal to y implies the image of x is less than or equal to the image of y. The elements are arranged in the natural order. The reason why we're using n is excluding the identity permutation. Let S be a semigroup, then an element E in S is called an idempotent if E is equal to E square. A non-idempotent element whose square is an idempotent is called quasi-idempotent. Let A be a subset of S. Then A is said to generate S if every element of S is expressible as a finite product of element in A. Then the rank of S, that is the rank of the semigroup, is the minimum size of A, such that A is a subset of S and A generates S. If the set of generators are idempotent, then it is called idempotent rank. And if the set of generators are quasi-idempotent, it's called quasi-idempotent rank. These identifications we use in this work, we have the height of alpha, that is the size of the image of alpha, and fix of alpha, the set of all points in the domain of alpha, so that the point is called its image. The shift of alpha, the size of the set of all points in the domain of alpha, so that the point is not equal to its image. We have the defect of alpha, that is the size of xm minus m alpha. We have the void of alpha, that is the size of xn minus domain of alpha union the image of alpha. And sin n, we refer to all those mapped in Tn so that the size or the height of the image is less than or equal to n minus 1. And we have kernel of alpha, that is 2 points in xn cross xn in the domain of alpha, such that the image of x equal to the image of y. And we have k and r is alpha belonging to sin n, such that the height of the image of alpha is less than or equal to r. And the range of r is 1 to n minus 1. So these are the related work we reviewed in the literature. Howe 1966 was the first to study generating element in full transformation semigroup, where he showed that the semigroup all singular transformations denoted by sin n is generated by the set of all idempotent of defect 1. Later in 1978, he showed that for n greater than or equal to 3, the rank of sin n equal to the idempotent rank of sin n equal to n minus 1 over 2. In 1966, he showed that n minus 1 idempotent of defect 1 generates sin n. And later, in 1978, he showed that half of them can generate sin n. Howe in 1971 was the first to study the semigroup of full order preserving transformations, where he showed that the semigroup of full order preserving transformations is generated by the set of all idempotent of defect 1 in On, and the size of On is 2n minus 1 combination n minus 1. Gomez and Howe in 1992 solved a rank problem in the semigroup of full order preserving transformations, where it was shown that for n greater than or equal to 2, the rank of On is equal to n. And for n greater than or equal to 2, the idempotent rank of On is equal to 2 into n minus 1. Here, the rank is not equal to the idempotent rank. But in sin n, the rank is equal to the idempotent rank. Garba, in 1994, generalized the result of Gomez and Howe in 1992 to the larger semigroup ONR. By ONR, we mean all those mapped in ON so that the height of the image of alpha is less than or equal to R, where he showed that ONR is generated by the set of all idempotent of height R for 1 less than or equal to R less than or equal to n minus 2. And the rank of ONR equal to idempotent rank of ONR equal to n combination R. Umar in 1993 was the first to use quasi-idempotent element in generating the set of all decreasing maps in symmetric inverse semigroup. Because he wanted to generate all decreasing maps in symmetric inverse semigroup, he found that idempotent element cannot generate IN because the idempotent form a subsemigroup in symmetric inverse semigroup. So he has to look for other generating set in the semigroup of all decreasing maps in symmetric inverse semigroup. He used quasi-idempotent element and they do the job. Umar showed that In minus, the set of all decreasing maps in symmetric inverse semigroup, is generated by the set of all quasi-idempotent of defect 1. And the rank of In minus, that is the set of all decreasing maps in symmetric inverse semigroup, is Nn plus 1 over 2. Garba et al. 2011 showed that the semigroup sin n is quasi-idempotent generated. That is, sin n can be generated by the set of all quasi-idempotent of defect 1. Before the work of Garba et al. 2011, it's only idempotent that was used to generate sin n, But in 2011, they showed that the quasi-idempotent element in Syn N can generate Syn N. And in the same article, they found that for n greater than or equal to 3, the quasi-idempotent rank of Syn n equal to the rank of Syn n, which is equal to nn minus 1 over 2, which coincide with the result of Gomez and Howe, which coincide with the result of Howe in 1978. Garba and Imam 2016 showed that the semigroup SIN of all strictly partial one-to-one maps in symmetric inverse semigroup can be generated by the set of all quasi-idempotent of defect 1. And the global quasi-idempotent depth of alpha in SIN is gravity of alpha, which is equal to shift of alpha plus void of alpha. And the global quasi-idempotent depth, that is the maximum number of quasi-idempotent required to generate the semigroup SIN, is the flow of 3 over 2 into n minus 1. Imam and Jamilu 2022 solved that problem in Syn N, where they showed that the set of all quasi-idempotent of defect 1 in Syn N is the ceiling of 1 over 2 gravity of alpha plus measure of alpha. And the maximum number of quasi-idempotent of defect 1 required to generate Syn N is n minus 1. So these are the related literature we reviewed, and after reviewing the related literature, we have found that apart from the work of Howe in 1971 and Gams and Howe in 1992, which showed that idempotence generates the semi-full order preserving transformation, there is no prior work that use order generating elements in generating the semi-full order preserving transformation. So in this work, we are going to use another type of generating element called quasi-idempotent to generate the semi-full order preserving transformation. But before we do that, we have to study the structure of elements in the semi-full order preserving transformations to see how they behave. Let OM be the semigroup of full order preserving transformation on Xn. Given a semigroup, the first thing that comes into our mind is how to characterize the Green's relations, because the Green's relation partition the semigroup into different layers. If alpha and beta belong to An, then by proposition 1.4.11 in Howe 1995, we have that alpha is unrelated to beta if and only if im alpha equal to im beta, and alpha is unrelated to beta if and only if the kernel of alpha equal to the kernel of beta, and alpha is J related to beta if and only if the height of the image of alpha equal to the height of the image of beta. Thus, On is a union of J classes, J1, J2, Jr up to Jn minus 1, where Jr are all those mapped in On so that the height of the image is equal to R. Thus, this is a diagram that shows how the J classes of On are arranged. We start from J1, J2, Jr plus 1 up to Jn plus 1. This Jn plus 1 is the topmost layer of the semigroup because we exclude the permutation part. So we want to pay particular attention to this J class Jn minus 1 at the top of the semigroup because it was shown that the element at the top of the semigroup generate the entire element in the remaining J classes. Associated with a mapping alpha in On is a digraph gamma alpha whose vertices are labeled 1 to n, and there is an edge I to j if and only if the image of I is equal to j. Let alpha be a map in On. We define an equivalence relation omega on Xn by the pair I comma j belong to Xn cross Xn so that there exists positive integers r and s so that the image of I to power r is equal to the image of j to power s. The omega classes are the connected component of the gamma alpha, of the digraph gamma alpha, called the orbits of alpha. And they are of two types. The one cycle called the trivial cycle, and or fixed point, and the acyclic orbits. Each orbit omega has a kernel. Omega defined by is I belong to omega so that there is positive integer r great, but there is positive integer r so that the image of I to power r is equal to I. You can see this is a cycle. This kernel of the omega is a cycle because I alpha to power 1 to power 2 up to power r is coming back to I. To see that the kernel of the orbit is non-empty, for each orbit omega, consider an element I in the orbit. The elements I I alpha square cannot all be distinct. They are not distinct because the same group is finite. And so there exists m greater than or equal to 0 and r greater than or equal to 1, such that the image of I to power m plus r is equal to the image of I to power m. Thus, the image of I to power m belong to the kernel, that is the cycle. And orbit omega is said to be, so in full order preserving transformations, we have two types of orbits, the trivial ones and the acyclic one. The orbit is acyclic if and only if 1 is equal to the size of the kernel of the orbit, which is less than the size of the orbit. And the orbit is trivial if and only if 1 equal to the size of the kernel of the orbit, which is equal to the size of the kernel of the orbit, which is equal to the size of the orbit. We now give an example. For n equal to 14, we consider this map. From this map, we can see that we have two types of orbits. This orbit and this orbit are acyclic, while this one are the trivial ones. And orbits are represented in the diagram below. This is an acyclic orbit because the size of this orbit, the size of the kernel of this orbit is 1. Likewise, this one, the size of the kernel is 1. And this is the size of the orbit, the size of the kernel, which is 1. The semigroup ON is aperiodic. That is, the H class contains singleton element. That is, it has trivial H classes. And the kernel classes are convex subset of Xn, in the sense that for every xy belong to C, x is less than or equal to y less than or equal to z, x is less than or equal to z less than or equal to y implies z belong to C. So by convex, we mean if x and y belong to C, we cannot have a point between x and y unless it is arranged in a natural order. We want to pay particular attention to the J class Jn-1 at the top of the semigroup. Why Jn-1? Because the element at the Jn-1 generate the entire element in the remaining J class. Thus, denoting by Ij the equivalence on Xn, whose non singleton class is Ij. We see that the R classes in Jn-1 are indexed by n-1 equivalences, n(n-1), n-2, n-1 up to 1 and 2. And the L classes, the number of the L classes correspond to the n possible images. That is xn minus n, xn minus n minus 1 up to xn minus 1. Thus, the size of Jn minus 1 in full order preserving transformation is n into n minus 1. So here we study the structure of element in Jn minus 1. There are two types of element in Jn minus 1, the increasing elements and the decreasing elements in Jn minus 1 of the full order preserving transformation. We start with the decreasing elements. The element with the non-trivial kernel I plus 1 and the image xm minus k. This xm minus k is the defect set of the map. It's a decreasing element if k is greater than or equal to I. And alpha is written in array notation in this form. From this map, you can see that the only missing point in the image of alpha is k. And this k is less than or equal to, is less than I. Sorry, is greater than I. So the mapping is a decreasing map in Jn minus 1. We now give an example. Let n equal to 9. We consider this map. From this map, we can see that when we look at the image set, the only missing point in the image is 6. And our I is 3, our I plus 1 is 4. So our K is 6. Thus, K is greater than I. And so this map is a decreasing map in full order preserving transformation in Jn minus 1. The element with the kernel I plus 1 and xm minus k is an increasing element if k is less than or equal to I. And alpha is written in this form. When we look at the image set of this map, we can see that the only missing point is k. And this k is less than I because here is our I and I plus 1. So k is less than I. And so the map is a decreasing, is an increasing element in Jn minus 1. This we represent alpha in linear notation, and this linear notation was introduced by Liscombe in 1992. You can see that the map is an increasing k to k plus 1, k plus 2 up to I to I plus 1. Let n equal to 9. We consider the map. So this is our map. We can see that we have 3 to 4, 4 to 5, 5 to 6, and 6 to 6. The other element are fixed. Our I and I plus 1 are 5 and 6. and our k is 3. Thus, k is less than I, and so the mapping is an increasing map in Jn minus 1. Our main goal is to show the rank. So now we have the increasing element and we have the decreasing element. So our main goal is to show the rank and the idempotent rank of full order preserving transformation. But we have to know what is the behavior of those idempotent in Jn minus 1. The map with the kernel ii plus 1 and the image xm minus k is decreasing idempotent if the missing point in the image is I plus 1. And alpha is written in this form. From this map, we can see that the only missing point in the image is I plus 1. And so alpha can be written in this form, I plus 1 to I. This mapping is showing that all other elements are fixed. Thus, we denote alpha equal to I plus 1 to I for I starting from 1 to n minus 1. We now give an example of this map for n equal to 9. When we consider this map, we consider the only shifting point here is 65. All other elements are fixed. And the missing point in the image is 6, that is our k, which is equal to I plus 1. So this map is a decreasing map in J, is a decreasing idempotent in Jn minus 1. Also, the map with the kernel ii plus 1 and the image xm minus k is increasing idempotent if k equal to I. That is, if the missing point in the image is I. From here, we can see I plus 1, but we don't have I in our image. So this map can be written in this form, I to I plus 1. And so alpha can be written I to I plus 1 for I starting from 1 to n minus 1. So this is an example where we have the only missing point is 5, which is our I. So this map is an increasing idempotent in Jn minus 1. So from these explanations, we can see that there are n minus 1 increasing idempotents in Jn minus 1 of the full order preserving transformations denoted by I to I plus 1 for 1 to n minus 1, and n minus 1 decreasing idempotents denoted by Fi for I plus 1 to I, and I starting from 1 to n minus 1. Thus, if QE1 is the set of all idempotent of defect 1 in the full order preserving transformations, then the size of the idempotent of defect 1 in full order preserving transformation is equal to 2 into n minus 1. From Howe 1971, it was shown that ON is generated by the set of all idempotent of defect 1. And in Gomez and Howe 1992, it was shown that the rank of ON is equal to n, and the idempotent rank of ON is equal to 2 into n minus 1. Also, ON is generated by the set of all E1 to En minus 1 and gamma. What are these EIs? They are the set of all increasing idempotent in Jn minus 1. And gamma is a strictly decreasing map in Jn minus 1. Thus, for any A subset of Jn minus 1 in the full order preserving transformation, we have that On is generated by A if and only if the set of all increasing idempotents and gamma are subset of the semi group generated by A. So Gomez and Howe showed that when this equality holds, then that subset of Jn minus 1 generates the full order preserving transformation. So in our work, we want to express this increasing idempotence and gamma as a product of quasi-idempotence in Jn minus 1. So here we present our main results. In this section, we study the nature of quasi-idempotence in the semi-group full order preserving transformations, and we showed that we said that the same full order preserving transformation is quasi-idempotent generated, and we later found the bound for quasi-idempotent rank of On. Each element alpha in On with image sets B1, the image are arranged in natural order, and a map alpha in On can be written in array notation in this form: A1 to B1, A2 to B2, up to AR to BR, where the capital A1, they are the kernel classes of alpha, and they are arranged in a natural order, and the B1 to BR, they are the image of alpha, and them two are arranged in a natural order. The kernel classes are convex. We initially said that the kernel classes are convex. That is, A1 is less than A2, less than A3, up to less than AR. Here, AI is less than AJ, mean any element AI less than aj for all, we mean any element in ai is less than an element in aj in the next j class. Each of these kernel classes is called a block of alpha. So we now give this definition. For the map alpha in on, a block ai of alpha is called stationary if it contains its image. Otherwise, it is called a non-stationary block. So this theorem characterizes quasi-idempotent in full order preserving transformation. By this theorem, I can be able to identify all quasi-idempotent in the same or full order preserving transformation. An element alpha in On is quasi-idempotent if and only if the image of each non-stationary block of alpha is contained in a stationary block of alpha. That is, give me a map. If I see that all the non-stationary block of alpha are mapped into stationary block of alpha, then that map is a quasi-idempotent. That is, when I square that map, I'm going to obtain an idempotent. So we now give an example. Let n equal to 11, and let alpha be this map. This map has block 1 and 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. You can see that the first block is stationary because it contains its image. The second block is not stationary because it did not contain its image. The third block is also stationary because it contains its image. Likewise, this block is not stationary because it did not contain its image. This block is stationary because it contains its image, and this block is not stationary. But we can see that all the non-stationary blocks are mapped into stationary block. Like this block is not stationary, but it mapped into this block, which is a stationary block. This block is not stationary, but it's mapped into a stationary block, that is 5 and 6. Also, this block is not stationary, and it is mapped into a stationary block, which is 9 and 10. You can see that when we square alpha, we obtain an idempotent. In idempotent, all the blocks are stationary block, because the image is among the pre-images of the map. Here, the image is contained here. The image also is contained. So alpha square is an idempotent. We now give a counter example of beta, which is not a quasi-idempotent. So we have the following blocks: 1 and 2, 3, 4, 5 and 6, 7 and 8, 9 and 10. You can see that the first block is stationary, the second block is not stationary, but it is mapped into the first block, which is a stationary block. The third block, 5 and 6, is also a non-stationary block, and it is mapped into another non-stationary block. This block, 7 and 8, is not stationary, and it's mapped into another non-stationary block. Likewise, this block is stationary. You can see that beta square is not quasi-idempotent because some of the blocks are not fixed by beta square. So beta square is not a quasi-idempotent. So we now restrict ourselves to Jn minus 1. An element, we now have the following corollary. An element alpha in On of height n minus 1 is quasi-idempotent if and only if shift of alpha equal to 2. So in Jn minus 1, all those elements in which shift of alpha equal to 1, they are the idempotent. And all those elements in which shift of alpha equal to 2, they are the quasi-idempotent. From this corollary, it is clear that in On, an element alpha in Jn minus 1 with kernel ii plus 1 and the image xm minus k is quasi-idempotent if and only if the missing point in the image is I minus 1 or I plus 1. In the former, when the missing point is I minus 1, then that map is an increasing quasi-idempotent, which is written in this form: I minus 1 to I to I plus 1. I minus 1 is called the lower entry, I is called the middle entry, and I plus 1 is called the upper entry of the map, where I start from 2 to n minus 1. In the latter case, when the missing point is I plus 1, then that map is a decreasing quasi-idempotent, which is written in this form: I plus 1 to I and I to I minus 1. And I starting from 2 to n minus 1. Thus, if QE1 is the set of all quasi-idempotent of different 1 in On, then the size of quasi-idempotent of different 1 in On is 2 into n minus 2. So for each I starting from 2 to n minus 1, let delta I be the set of all increasing quasi-idempotent. So anywhere we see delta I, they are the set of all increasing quasi-idempotent, and mu I, they are the set of all decreasing quasi-idempotent. Then it is clear that the kernel of delta I is I plus 1, the kernel of mu I is I minus 1I, the image of delta I is xn minus I minus 1, and the image of mu I is xn minus I plus 1. And that's QE1. Therefore, our quasi-idempotent in Jn minus 1 consists of the increasing quasi-idempotent and the decreasing quasi-idempotent for I starting from 2 to n minus 1. We now have the following theorem. For n greater than or equal to 4, the semigroup of full order preserving transformations is generated by the set of all quasi-idempotent of defect 1. It was shown, if you can remember, it was shown by Gomez and Howie in 1992 that a subset A of Jn minus 1 generate On if and only if the set of all increasing idempotent and gamma are subset of the system group generated by A. Here, we express our increasing idempotent and gamma in terms of the quasi-idempotent of defect 1 in Jn minus 1. And therefore, by the result of Gomez and Howe in 1992, the quasi-idempotent in Jn minus 1 generate the full order preserving transformations. This lemma, we are taking the product of any element alpha and beta in Jn minus 1. We want the product alpha and beta to be in Jn minus 1. Let n greater than or equal to 4 and alpha belong to Jn minus 1 minus the set of all quasi-idempotent of defect 1 union the idempotent of defect 1. And beta belong to the quasi-idempotent of defect 1 union idempotent of defect 1. We want the product alpha beta to be in Jn minus 1. Then alpha and alpha beta, they are either both increasing or both increasing. First, we note that any generating set in the full order preserving transformations must cover both the L classes and the R classes in Jn minus 1. Also, since On has n L classes and has n minus 1 R classes, then it follows that any generating set must not be less than n, that is the number of the L classes. So n is less than or equal to the quasi-idempotent rank, and this 2n minus 2 is the size of the quasi-idempotent because we are looking at the minimum number of quasi-idempotent required to generate the full order preserving transformation. So the minimum number is either less or equal to the number of quasi-idempotent in Jn minus 1. So we now have this theorem. Let n equal to 4 or 5. We have the quasi-idempotent rank of On is equal to 4 if n is equal to 4 and is 6 if n equal to 5. How? If n equal to 4 or 5, we have, if n equal to 4, we have the set of all quasi-idempotent in all 4 when equal to 4, we have 4 of them. Mu1, mu2, that is the decreasing quasi-idempotent and the increasing quasi-idempotent. And these are alone in either of their L classes or R classes. And so no fewer number of quasi-idempotent will generate O4 when n equal to 4 because the generating set must cover both the L classes and R class. And if n equal to 5, we have 6 of them, 3 increasing quasi-idempotent and 3 decreasing quasi-idempotent. And no proper subset of QE1 covered both the L classes and the R classes. So the quasi-idempotent rank of O5 is 6. Now, for n greater than or equal to 6, the quasi-idempotent rank of On is equal to the ceiling of 3 over 2 into n minus 2. Here, we look at when n equal to 6 and above and see in that J class Jn minus 1, we have the size of the quasi-idempotent is 2 into n minus 2. So we look at the set of the quasi-idempotent to see which one among them are redundant, which one can we remove among the set of all quasi-idempotent, or which one among them are not alone in either in their L classes or R classes. So we try to remove all those ones that are not alone in either of the L classes, and we see that all those ones can be expressed as finite product of other quasi-idempotent in Jn minus 1. And therefore, we reduce the number of quasi-idempotent in Jn minus 1. And the problem is in two stages, the even case and the odd case. Finally, we found the upper bound of quasi-idempotent rank of On to be the ceiling of 3 over 2 into n minus 2. Remark, We suspect that the upper bound for quasi-idempotent rank of ON found in Theorem 13 is best possible. That is, no pure number of quasi-idempotent will suffice in generating ON. Currently, we are able to provide the proof, that is the converse case, necessary and sufficient condition. These are some of the selected references. The result of this work was published by the Journal of Algebra and Discrete Mathematics, volume 35, issue number 1 of 2023. Thank you for listening.
Thank you very much. So, Chairman,
Thank you for the presentation. I've lost. I thought the presenter is not Sagri, it's AT Imam. And when AT Imam was presenting, I thought it was Professor Giu Garba. Thank you for the presentation. In fact, I didn't expect that you would present beautifully like this. I wish you a very successful completion of your thesis and program. May God continue to be with you and everyone here present. Thank you for the presentation. The only observation I have